We now move into the final major part of Week 1, Carbon Capture and Storage, or CCS. This section is very important because the future of petroleum engineering is increasingly connected to decarbonization, subsurface storage, and environmental stewardship. In this course, we treat CCS not as a separate topic, but as a natural extension of subsurface engineering expertise. One of the biggest environmental concerns associated with fossil fuel use is anthropogenic climate change. When carbon-based fuels are burned, they produce CO2 and other emissions such as carbon monoxide and nitrogen oxides. This does not mean petroleum engineering becomes irrelevant. Instead, it means the discipline must evolve and contribute solutions. That is where carbon capture and storage becomes a key topic for the next generation of petroleum engineers. This slide is a discussion prompt. Why do you think Asia's CO2 emissions have increased so strongly in recent decades compared with some other regions? This is a great teaching moment because the answer is not one factor, it is a system-level combination of industrialization, population growth, economic development, energy mix, and global supply chains. Several factors explain the increase. Rapid industrialization has expanded manufacturing and energy demand. Population growth and urbanization have increased demand for transport, housing, and infrastructure. Economic growth has increased consumption of energy-intensive goods and services. Another major factor is Asia's role in global supply chains. Many products consumed worldwide are manufactured in Asia, so part of the associated emissions are concentrated in producing countries. In addition, the energy mix in many regions still depends significantly on fossil fuels, especially coal in some countries. This is why decarbonization strategies, including CCS, are increasingly important. Now let's define CCS. Carbon capture and storage is a set of technologies used to capture CO2 from industrial sources, transport it, and store it safely in deep geological formations to prevent its release into the atmosphere. CCS is especially important for sectors that are difficult to decarbonize, such as cement, steel, chemicals, and some hydrogen production pathways. For petroleum engineers, CCS is highly relevant because many required skills, subsurface characterization, drilling, well integrity, reservoir simulation, and risk management are already core competencies in our field. This slide introduces the capture step of CCS. One common method is chemical absorption using solvents such as amines, which selectively absorb CO2 from gas streams. After capture, the CO2 is typically purified, compressed, and prepared for transport. The key point here is that CCS is a chain, not a single technology. Capture performance affects transport design, and transport conditions affect storage injection strategy. This slide introduces geological storage. Injected CO2 is stored in deep subsurface reservoirs, typically porous rock formations such as sandstone, beneath an effective sealing layer called caprock. The caprock prevents upward migration, while the reservoir provides pore space for storage. Over time, several trapping mechanisms can improve storage security, including structural trapping, residual trapping, dissolution, and sometimes mineralization. This is where petroleum geology and reservoir engineering directly support climate solutions. Caprock is one of the most critical elements in geological CO2 storage. To store CO2 safely, we need a caprock with strong sealing capacity, sufficient thickness, and broad aerial coverage over the reservoir. Fine-grained rocks such as mudstone often serve as caprocks because their permeability is very low. In practice, CCS site screening includes careful evaluation of caprock integrity, faults, fractures, and geomechanical behavior to reduce leakage risk. Now we focus on the reservoir itself. Suitable reservoir rocks, such as sandstone and some volcanic rocks, must provide enough pore space to store CO2 and enough connectivity to allow injectivity. The blue highlighted spaces in this slide represent pore volume where CO2 can be stored. This slide is a nice bridge to reservoir engineering concepts. Porosity controls storage capacity, while permeability influences injection rate and pressure buildup. CCS is important for several reasons. First, it can reduce greenhouse gas emissions from large point sources. Second, it complements renewable energy by helping decarbonize sectors where direct electrification is difficult. Third, many climate pathways indicate that meeting climate goals becomes much harder without some form of carbon capture and storage. For engineering students, the key idea is this: CCS is not a replacement for all solutions, but it is a major part of a broader decarbonization portfolio. CCS also faces major challenges. These include high costs, infrastructure requirements, public acceptance, regulatory uncertainty, and the need for long-term monitoring and risk management. Subsurface risks such as leakage concerns, pressure buildup, and induced seismicity must be carefully studied and managed. This is exactly why strong petroleum engineering and geoscience expertise are essential for CCS deployment. This is one of the most important slides in the course. Petroleum engineering can support CCS across the full chain: upstream knowledge of subsurface geology and wells, midstream infrastructure expertise for transport, and downstream integration with industrial systems. Existing petroleum facilities, workflows, and engineering skills can often be adapted to lower CCS costs and improve project safety. So rather than seeing petroleum engineering and climate action as opposites, we can see petroleum engineering as a powerful enabler of practical decarbonization. This slide summarizes the global status of CCS using project counts and capture capacity indicators. When presenting this slide in a Udemy course, I recommend emphasizing trends rather than only memorizing numbers. The key message is that CCS is expanding, with growing project pipelines and increasing international interest. Also, remind you that these numbers are time-sensitive and should be updated when the lecture is recorded or revised. Here we focus on Japan's CCS direction and policy momentum. Japan is positioning CCS as part of its broader pathway toward carbon neutrality and energy security. This makes Japan an especially interesting case for students because it combines industrial demand, offshore and subsurface opportunities, and strong engineering capability. This slide introduces a CCS demonstration workflow in Japan. CO2 is captured from refinery-related hydrogen production, purified, compressed, and transported to an injection site, where it is injected into subsurface reservoirs. The important lesson is process integration, capture, purification, compression, transport, and storage must all work together as one engineered system. Students should notice that petroleum engineering skills support the storage end, but the full CCS chain requires collaboration across chemical, mechanical, civil, and systems engineering. This slide raises a critical real-world question. Why might a CCS project be suspended or delayed? In practice, project continuity can be affected by technical issues, public perception, regulatory concerns, economics, or geohazard concerns such as seismicity. This is an excellent slide for teaching engineering responsibility. A technically feasible project still requires social trust, monitoring transparency, and careful risk communication. This slide highlights the importance of understanding subsurface behavior, including pressure changes, deformation, and possible seismic responses during or after injection operations. Whether or not events are directly attributable to injection, engineers must evaluate pressure propagation, fault conditions, and monitoring data carefully. This reinforces a central theme. Subsurface energy projects require not only injection design, but also geomechanics, monitoring, and risk-informed decision-making. This slide shows the full CCS chain: capture from power plants or industrial processes, transport by pipelines or ships, and geological storage in formations such as depleted oil and gas reservoirs or deep saline formations. In this course, our main focus is the geological storage part, the subsurface component, because this is where petroleum engineering concepts such as reservoir characterization, injection design, and containment become central. This focus helps you see how their petroleum engineering foundation can be directly applied to low-carbon technologies. This slide presents the Sleipner project in Norway, one of the most well-known and successful industrial CO2 storage projects. Sleipner is a landmark example because it demonstrates long-term CO2 injection into a saline aquifer and uses monitoring techniques such as time-lapse seismic imaging to track plume migration. For you, Sleipner is an excellent case study showing how geology, monitoring, and reservoir engineering come together in a real CCS project. This slide introduces the Nagaoka CO2 storage project in Japan, a pilot-scale demonstration conducted in a shallow sandstone aquifer at around 1,100 meters depth. The cumulative injected CO2 amount and the project timeline make this a valuable Japanese case study for understanding storage feasibility, monitoring, and site-specific geology. In research, it is useful to compare Nagaoka with Sleipner. Both are important, but they differ in scale, geology, and context. This slide summarizes three major technical challenges in geological storage: injectivity, storage capacity, and containment. Injectivity tells us how easily CO2 can be injected without excessive pressure buildup. Capacity tells us how much CO2 can be stored. Containment tells us whether it can remain safely trapped over long periods. The slide also points toward reservoir simulation as a key tool. This is exactly where petroleum engineering methods become essential for screening, design, optimization, and risk assessment. We have now completed all major parts of Week 1, Petroleum Fundamentals, Industry Structure and Status, and an introduction to carbon capture and storage. Before moving on, I encourage you to review the terminology petroleum, hydrocarbons, source reservoir caprock, pressure gradient, geothermal gradient, and oil/gas window, because these concepts will continue appearing in future lectures. Let's now recap what we learned in Preview the next week. In Week 1, we covered the definition of petroleum, basic geology concepts related to petroleum systems, the structure of the petroleum industry, and the role of CCS in modern petroleum engineering. This foundation is important because it prepares you to understand more technical topics in the coming weeks. Next, we will go deeper into petroleum geology and begin building the geological framework needed for exploration and reservoir evaluation. If you have questions, please write them in the course discussion area. I encourage you to ask both technical questions and conceptual questions, especially if something is unclear in the geology or CCS sections. In the next lecture, we will continue with petroleum geology. Thank you, and see you in the next class.